Shalom Aleichem, Boker Tov, California, Erev Tov, Laila Tov, the rest of the United States, and our dear friends in Israel. Good evening. My name is Bob Tandler, and I am the chair of the San Francisco Haifa Sister City Committee, a former member of the American Technion Society Bay Area Board of Directors, and I am honored to bring greetings today to you from our Sister City Committee, from the Israeli Consulate, from the San Francisco Mayor's Office of Protocol, the California Israeli Chamber of Commerce, who, along with the American Technion Society, are co-sponsoring today's program. I was delighted to be invited by the ATS to join you today to talk about something that is always front of mind, the future of our beloved planet. Having just celebrated Earth Day, it is fitting to continue the important discussion around sustainability and research that will tackle these global problems of the 21st century. Before introducing my colleague and our moderator, David Kaufman, I would like to take a moment to honor my dear friend and recently passed Bay Area philanthropist, sustainability champion, and Technion supporter, Stephen Grand, who passed away last month. Stephen was a second-generation Technion supporter. His father was president of the local Detroit chapter of the ATS and would, as Stephen used to recall, drag him around to Technion events. Well, Stephen dragged me around to a Technion event, which is how I got involved. As Stephen grew up, he used to say, I came to understand the crucial role that Technion has played in the survival and success of Israel. Stephen and his wife, Nancy, were honored as Technion guardians, those friends who made the highest commitment to the Technion, as they've realized that the world's future sustainability, economic development, and security depended upon answers to the technical and economic challenges faced by the water industry, as well as the development of reliable energy sources. Innovative research and technology were needed, so Stephen provided major support for the establishment of the Technion's Grand Water Research Institute and the Grand Technion Energy Program. In addition to their support for the Technion, Stephen and Nancy have been active in numerous philanthropic activities throughout the United States and Israel, and their presence at the Technion will be constant, but Stephen's will be sorely missed. I will be remiss if I don't acknowledge the recent tragedy at Mount Meron, and that we send our prayers to the victims of the tragedy and in their honor as we continue with our program. We want to thank you for joining us today. We have a wonderful program. I would like to now share a short video about the Technion.
This place is where diseases are cured, Nobel Prizes are won, and the technology that's making the world a better place is made. Welcome to the Technion, Israel Institute of Technology. Founded in 1912, 36 years before Israel's independence, it is one of Israel's oldest and most prestigious universities. One of its pioneers, Albert Einstein himself. Three Technion professors have won the Nobel Prize in chemistry. Dan Shechtman discovered something thought impossible, a quasi-crystal.
My research is centered on the structure and properties of metallic materials. Over the years, I have been developing different metallic alloys, and in recent years, magnesium alloys. In the future, we use the wonderful alloys that we have developed over the years and 3D print them to form useful structures.
Avram Hershko and Aaron Shechanover discovered the control mechanism of the protein in the cell, which is a huge leap for cancer treatment research.
I hope that in the future we shall see also drugs to combat other diseases like Alzheimer and other neurodegenerative diseases.
Professor Shulamit Levenberg is pioneering stem cell research here at the Technion.
We try to engineer pieces of tissues in the lab, and these pieces of tissue can then be implanted to repair or replace damaged tissues. In the future, we plan to take tissue engineering to its next level. We established the Bioprinting Center, and we can now print biomaterial and cells to build tissue that can be personalized and large-scale tissue, complex tissue.
here in Professor Hossam Chayek's laboratory. He has developed nanos, which, upon sampling a patient's breath, can diagnose up to 17 different diseases.
All my life, I have believed in equal opportunity for every life over Earth. And therefore, the next step in our research and development is to enable diagnostic tools that are very cheap, very affordable, that could be delivered to every person.
The Technion is not only a science powerhouse, but it's also an engine for coexistence. Over 20% of the student body are Arabs, the same proportion as there is in the overall Israeli population. Imagine life without fast internet streaming. Well, the Lempel-Ziv algorithm developed by Technion professors finds a way to compress data without losses. Now that's important when you're streaming your favorite TV shows. For over a century at the Technion, people from all over Israel, all over the world, have joined forces to solve some of humanity's greatest problems. If you care, share.
On that upbeat note, I'm now pleased to turn the program over to my friend and colleague on the San Francisco Haifa Sister City Committee, David Kaufman, Director of Global Strategies at Nixon Peabody and an American Technion Society Bay Area board members. Thank you, everyone, for attending. Please enjoy the show. David, it's yours.
Thank you, Bob. Thank you. That was a great video, really inspiring. I think that this is such an important topic. Clearly, climate change and clearly our planet is undergoing great changes here in California. We're going to be suffering another year of drought. We're worried about wildfires, but we're seeing the effects all over the U.S. and all over the world, frankly. The pandemic has been kind of interesting as far as that's concerned, in that we're seeing the return of flora and fauna around the world. As we've been all staying here, not going out as much, the air is cleaner. Nature has had a resurgence. I'm a runner and a cyclist, and I've seen that just on my daily runs. I've been hearing a lot more woodpeckers that are out in our neck of the woods, and I've seen a lot of animals have emerged. One of the interesting things we're going to hear about is that in Haifa, a really fascinating phenomenon is taking place where wild boars are roaming free. The boars have been increasingly carefree. I've even visited some of the buildings on the Technion campus. Part of our conserving our planet includes consideration of how to coexist with these animals. And one of our speakers, Professor Daniel Orenstein of the Technion's Faculty of Architecture and Town Planning, an advisor to the Technion Sustainability Hub, will join us today to talk about that, in addition to his work in and around Haifa as the principal investigator of the Socio-Ecological Research Group. Another important consideration when we think about the planet's future is industrialization, and Technion Assistant Professor Graham de Ruiter will shed some light on his research that he hopes will revolutionize industrial processes in the food, energy, and healthcare sectors using naturally abundant metals. Professor de Ruiter is head of the Technion's Laboratory for Inorganic and Materials Chemistry and the Schulich Faculty of Chemistry. He's also affiliated with the Grand Technion Energy Program, which we just heard about. His work in the area of catalysis, I have to say that word twice, will have an important and positive effect on the environment and the way we live. Finally, but also very importantly, how we feed the future inhabitants of planet Earth. Food's a very important topic. I think that, we've been going to grocery stores more often and, thinking about where our food comes from and trying to make it interesting and creative here as we've been at home under lockdown. But a huge factor in sustainability, of course, involves food. And Professor Ester Segal will discuss efforts to develop technological solutions for minimizing food losses and devising healthy alternative protein, both aimed at tackling looming food shortages. Esti heads the Laboratory of Multifunctional Nanomaterials at the Faculty of Biotechnology and Food Engineering, and is also the Technion's Deputy Vice President for Research. Thank you all for being here today. Just a reminder, we have time for questions after all of their guests speak. we'd like to use the Q&A function on the webinar stream to submit your questions. And we'll be monitoring that, and we'll try to get those to the speakers at the end of the program. So please put them in there. You know, if it comes to you, drop it into the Q&A. We will get to it. If we haven't gotten to it through one speaker, we'll do it. We'll definitely do it at the end. So please do that. So I'll hand it over to Daniel.
Thank you, David, and thank you everyone who's joined us today. As David noted, I have two hats at the Technion. I'm also a professor in the Faculty of Architecture and Town Planning, but I also serve as faculty advisor to the Technion Sustainability Hub. And the Sustainability Hub is the administrative unit on campus where we try to make policy to determine how the institution will behave environmentally. And we also try to promote all of the research and teaching that has to do with sustainability issues on campus. And we got a tremendous boost from the current president of the Technion, who in his opening address when he took the position, noted that there are 6 grand challenges facing academia, facing the world and facing academia, 2 of which are environment and sustainability. And with that, he gave the Technion the push forward to address these complex interdisciplinary issues and also help push our agenda forward in the Sustainability Hub. And if you note the quote at the top of the screen, the Technion's vision, that we're a science and technology research university stressing our contribution to the advancement of the state of Israel and all of humanity. That is, we do what we do to try to improve human life on the planet and use our technologies and our knowledge to promote human well-being. So before I go on, let's define first what sustainability actually means. It's one of those words that a lot of people know, but very hard to define. I start by talking about what sustainability is not. And what sustainability is not is pushing the capacity of the planet to support human life beyond its abilities. So if we look at issues like climate change, biodiversity loss, or nutrient accumulation in the environment and our waterways, we have 3 examples where human activities are pushing ecological limits beyond their capacity to give humans what they need for living well on the planet. So when we talk about sustainability, we're talking about 2 things that are actually very well summarized in the economist Kate Raworth's diagram of donut economics. We're talking about human well-being in the center ring, assuring that humans need all those things, not just food and water, but material well-being, security, equality, and freedom. We need all of those things to assure a good life, but we have to somehow work it out so everyone on the planet can get those things without pushing beyond the ecological limits of the planet. And that can express itself in climate change, in biodiversity loss, in land conversion, etc. So when we talk about sustainability, we're talking about assuring human well-being within the capacity of the planet to provide for humans. With that, I'm going to jump into my research program. I'm a social ecologist. That means this is my world. This is the interconnection between human social systems and the biophysical system. So environmental issues are central to that. And particularly looking at how human activity impacts the biophysical system and how the biophysical system responds in conditions for human life. So we can impact the system for the better, as in when we cultivate fields to increase our agricultural output, we can increase biomass, increase food production, but that might come as an expense of additional nutrients in our waterways, or increased pollution, or increased carbon dioxide, and that affects the human system, and we have to respond accordingly in this kind of cycle of feedbacks between the human system and the biophysical system. One of the most romantic ways that I'm looking at the interaction of these two systems is the presence of wild boars in the city of Haifa, and how humans respond to the presence of wild boars. Now, this isn't a particularly unique problem. In Southern California, you have your mountain lions, and in Colorado, you have your black bears, and on the East Coast, you have deer. In South Africa, you have baboons. And across Europe, you have more wild boars. And in each city, they have to understand, well, what is it that we want with the presence of these animals? Because in some cases, we can really enjoy their presence. This is my neighborhood on Yom Kippur, no cars, lots of kids on bikes, and a family of wild boar that joined us for the festivities. This is a wild boar that found his way into a kiddie pool somewhere in my neighborhood as well. And these I photographed earlier. That is, we can be romanticized by the presence of wild animals within our urban communities. It makes up, it compensates for our detachment from nature in almost every other way as we expand our cities and expand our energy, use of land for energy and for agriculture. So here we have nature coming back into the city, and that can be a very rewarding thing in light of the fact that we have a biodiversity crisis on the planet. On the other hand, it poses a certain amount of threats to us, whether that's a threat to our physical or biological well-being, just problems with sanitation in the city and turning over garbage bins, or ruining our gardens by burrowing for looking for roots and insects and whatever else the boars like to eat. Now, because there's these two different perspectives, policymaking becomes quite difficult, because you have to find the best way in a democratic society to deal with a problem that people have very passionate and often conflicting opinions about. Now, I worked with my students. I sent my students out into Haifa to interview people, to talk to experts in the field, and come up with a list of policies that the city can enact to try to separate between wild boars and humans without having to resort to poisoning or killing or culling or any of those things. And these are the things that my students came up with. And I want to emphasize here that it's actually a policy of ours to get our students out into the communities where they can offer their knowledge, in our case, of development of policy, to contribute to the well-being of the community. And in our case, the city actually adopted policies very similar to what our students were recommending. Another way we get our students out in the community is, in this case, a student is working with us from industrial design to design a boar-proof trash can. That is, we want to have trash receptacles that the boars can't open, that people can, at the same time trying to keep crows and cats out of our trash cans. So the student working on this project designed for us a solar-powered trash can that opens with a wave of the hand, because in the Corona era, we don't want people touching, but the can had to be closed. So this is what she designed for us, and we're gonna actually build a model of it and try to get a sample out into the field and see how it works. A couple minutes regarding our sustainable campus and what we want to do on campus. There are a lot of good reasons why a university should be at the forefront of sustainability issues. One, because we produce the knowledge on our campus. Two, because our job is to prepare the next generation with all the knowledge that we can accumulate and develop and pass it on to the next generation of researchers, of global citizens. And the third is because we're public institutions, many of us, and we owe it to society to be good civic actors. That expresses itself in three ways at the Technion: through the Sustainable Campus program, through our research, through our teaching, and importantly, through our institutional behavior. And I emphasize that because it's the hardest one to achieve. We do research and we know how to do it well, and you'll see several examples of it today. We know how to teach as well, and our teaching is is cutting edge on sustainability issues. Where we have a greater challenge is actually bridging the gap between what we know we should be doing and what we're actually doing. And that's where Sustainable Campus comes in, the Sustainability Hub, currently working on moving the Technion towards greater and greater energy efficiency, using alternative energy sources. Right now, we're also working very intensely to lower the amount of waste coming out of the campus, and that's to try to encourage alternatives, whether those are technological or just behavioral changes. We're trying to lower this amount, for instance, of the 2 million disposable cups that we used in 2019. One of our goals is to bring that much further down. So those are the three emphases. Regarding research, we did a quick survey about a month ago asking which departments are doing sustainability research. We have a list now of 50 plus laboratories on campus that are working on different aspects of sustainability, and you'll hear 2 tonight. Among those sustainability topics are clean energies, sustainable materials, pollution, green architecture and planning, and science education and civic engagement. And the last 2 slides I have, emphasizing that interdisciplinary nature of dealing with these environmental challenges. And that's why we're very thankful to have the Grand Energy Program and the Grand Water Research Institute, which all 3 of the speakers tonight are associated in one way or another, places where they bring together scientists from different disciplines to deal with these complex issues. And of course, we should recognize that especially tonight, given the news we heard earlier. And finally, one of our goals is to get the students and the research out of the classroom, out of the Technion, and into communities. And we do that through the Social Hub, and we do that through Engineers Without Borders and the Global Engineering Program. And all of those engage students through coursework to do things in the broader community, like using their architecture and planning skills. Environmental policy is the example we do with my students, constructing solar heating units in Africa, monitoring air quality in Haifa, and other programs like this. So between the research, the education, and the behavior, we're hoping to do the best we can to promote sustainability issues, not just within the Technion and today, but in the broader community and far into the future. And with that, I'd like to welcome Professor Graham de Ruiter, my colleague.
Thank you very much, Daniel. It's really an honor to be here today. I've chosen my title to reflect not only the topic of tonight, but also to reflect, I think, is a vision for the future, not within the Technion, but I think also on a global scale. And I would like to talk about enabling technologies for shaping a sustainable future. And we heard earlier from Daniel already what sustainability means. And for me as a chemist, sustainability means that the atoms that I take from nature, from my surroundings, I use and later return in a similar fashion so they can be reused. So overall, I am neutral. But in order to understand these processes and understand if this is really true, I would like to take a short tour to see if this is actually true what we're doing currently. So, for instance, if we look at the human mass, which is present at the moment, we're about 0.0% of the total global biomass that we currently have. What does that mean, or what do we do actually with these things? So in the last 3,000 years, what we have done, we have basically halved the total amount of biomass on this, or the plant mass, I should say, on this planet. Besides that, during the last 3,000 years, we have more or less increased twofold the carbon dioxide emissions, as you can see also here on the slide. And overall, more or less, in the last 100 years, we have increased 100-fold the amount of man-made mass. And actually, there was a paper this year that demonstrated that we have reached a critical milestone. And this milestone is that for the first time ever, the human-made mass exceeds the total amount of biomass on this planet. Now, this wouldn't be a problem if we have been able to do this in a sustainable fashion. What do we mean with that? We can look at some examples. So if you look or on the screen, at the moment, the amount of plastic that we have generated in the last, let's say, 50 years, at the moment exceeds all plant and also all animal mass on the planet. And this is actually a terrible foresight what is projected for the future when we increase the amount of plastics we use every day. And be reminded that most of these plastics are non-recyclable. On average, one's body weight, regardless where you're on the planet, is being produced in unsustainable mass. Mass meaning that cannot be returned to nature and cannot be reduced. And this is per week. So I think that these examples really demonstrate that we're not really on a sustainable path towards the future. And this can also be demonstrated that nowadays, if you can see in this other graph here, that the amount of buildings and infrastructure that we have at the moment exceeds all the trees and also all the plant mass that we have. So there is indeed a fundamental problem. So where do we get all these materials? Is that also in a sustainable way? And actually, it's shocking to find out that this is not the case. For instance, if we look here, I took a picture of the effect of mining operations on diverse ecosystems. So you can see here clearly on the screen, on the background, we have a nice mountain with nice flora and fauna. But what we see here at the bottom is what happens when we start mining. I'd like to pay attention to this little small unit over here, which is actually a gigantic truck trying to haul all the mining and all the ore away. So you see that now we are devoid of life and ecological systems, which is a very bad development. So now when we have generated all these mass and we took it, what do we do with it? Actually, we produce very bad, uncontrolled waste streams. And perhaps this little boy, and I don't know where it is smiling, but this picture doesn't make me smile because I see a lot of waste being dumped in nature, not recyclable and staying there perhaps for hundreds of years. And this is not very sustainable, at least not in my point of view. Nonetheless, even if we are able to do something useful with it, for example, in the production of pharmaceuticals, which I think you all understand are very important, is that you see that 1 kilogram of pharmaceutically active ingredient at the moment produces about 100 to 500 kilograms of waste, which cannot be reused. And typically it is being dumped at storage sites until they are being taken up by nature or pollute the environment. So just to summarize that, I think that we can all agree that current human endeavors are not very sustainable. The current methodologies that we have are not sustainable either. So what we see is that we generate enormous amounts of waste with large ecological destruction, which is not very good. And I really like to highlight again the amount of plastic that we have generated compared to the total amount of animal mass that we have nowadays. Another frightening fact is that whatever we are taking from nature nowadays, we return in a non-sustainable fashion, meaning nature cannot reuse those materials again to build up useful products. And this is something that what makes nature sustainable is nature takes, for instance, solar light, takes small raw chemicals, convert it to useful chemicals, uses it and returns it again in a way that so that nature can reuse it again. Besides that, the supplies that we have nowadays are already very limited. Fossil fuels, the amount of fossil fuels are diminishing and we're just using it to power our cars while you have much better uses for it. We also are running low on precious metals. So there is really a need to develop sustainable processes and convert waste streams into renewable resources. And one thing that we need for that, and that's where I come in as a chemist, is we need catalysis. So for those who are new to the area, what is catalysis? So one thing is that I learned while being Dutch is that nothing in this life comes for free. So meaning if you want to convert one material to another, you need to cross a certain energy barrier. And that's reflected by going over this mountain. So you can see if you want to convert one material to another, you have to you have to use an enormous amount of energy to get to your destination. But what if I tell you that I can, as a chemist, hire a secret contractor, as it were, to go through the mountain? And when I can go through the mountain instead of go over the mountain, I use much less energy. I can control the processes. And this is exactly what a molecular catalyst does. It provides me with a shorter route, which is more sustainable and more environmental friendly. At the moment, catalysis, for instance, is the #1 value generator in the chemical industry. For instance, catalysts alone generate about 900 billion in turnover. But besides that, catalysts also influences many different areas, such as healthcare, economics, the environment, and demographics. Just for you to know is that 80% of all products on the market nowadays at least contain one catalytic step in the manufacturing process. And I'd like to just imagine for a moment, if we can control this process at the molecular level, what kind of advantages we can gain. For instance, we can look at food engineering, crop protection, and biocatalysis. And the next speaker, I think, Segal, will talk about this in much more detail. I would like to remind, at least in one process, which is called Haber-Bosch process, which provides fertilizers so crops grow better in the ground, that at the moment, at this process, is being used on such a massive scale that 50% of all the nitrogen atoms in your body comes from this industrial process. And this process uses 2% of the world energy and creates large emissions of carbon dioxide. So if we can replace this with an even more sustainable process, there are huge advantages to gain. We can also look at waste streams, for instance, plastic conversion and clean energy technologies, so that we're not at the beach anymore where we have huge amounts of plastic, but we have clean beaches that we can ensure and entrust our children with to take care of. And at the moment, we're already developing technologies, for instance, that can take nylon polymers and convert them back to their starting material so we can reuse it again. We are also interested in developing new reactions and catalyst development so that not only we generate much waste, but we generate new materials that are more sustainable, that can be recycled. You can think about biopolymers or bioplastics, for instance. And we can also look at carbon capture. The Elon Musk Foundation has recently launched a $100 million program to take carbon and convert it back into a reusable form. And this is all done through catalysis. So you see that catalysis, for me as a chemist, is not only chemistry, but it addresses health, energy, earth, materials, and many other different processes. And this is actually precisely where my research comes in, because what my research does is that we contribute to sustainability by looking at nature. Now, nature, as you can see here on this graph, really uses earth-abundant metals, such as manganese, iron, chromium, and many more, nickel, copper. What we do nowadays in the chemical industry is using precious metals such as platinum, iridium. And these metals have very limited deposits. For instance, they have deposits of less than 0.001 milligram per kilo. That's why we need to mine large areas of land in order to get those metals. They are typically environmental friendly because it takes a lot of energy to extract them, to refine them, and utilize them. In recent years, those metals have become very expensive. The palladium price has skyrocketed. Perhaps that's the reason in the US why you see a very large increase that people steal catalytic converters out of their cars because it contains palladium. And these metals are toxic and being released in the environment when they're done. In my lab, we take a different approach. We take earth-abundant metals. Earth-abundant metals, as you can see here on the screen below, is that they are readily available. Typically, they are more than 50 grams per kilo. They're environmental friendly because iron is also contained inside our bodies. It's cheap. Typically, it's less than $0.01 US per gram, and they're non-toxic. So there are a lot of advantages that one can use. So what do we try to do in my lab? We try to take carbon capture and formation of liquid fuels from CO2. Can you imagine that you drive your car, you generate CO2, and we can take the CO2 again and convert it back to liquid fuel? So you have a closed cycle so that you can run your car forever. We're also looking at iron catalyzed formation of labeled pharmaceuticals. Meaning is that we're trying to devise new processes so we can specifically label positions at molecules so you can use it as radio tracers and therefore avoiding precious metals that are inside your body, for instance, that are being used. We also look to use iron in particular for industrial relevant processes? Can we replace those toxic and dangerous metals with environmental ones? So when we generate some waste, we can generally release it back to nature without any of the harmful side effects. Now, these are just a short overview of what we're doing in the research in my laboratory that is focused on inorganic and materials chemistry. But I'm not the one who's really doing it. The real heroes are shown here below, which is my team, who's making great progress. And with that, I hope to have shared with you the importance not only of my research program, but I think the entire vision of the Technion, that we really go into a more sustainable way and that everyone from different departments works together to contribute a little bit of areas, and together as a whole, we can make a great difference. And I think with that, who also is making a very great difference in terms of food engineering, I think is Professor Segal from Biotechnology and Food Engineering will be the next speaker. So please, Esti, go ahead.
Thank you very much, Graham, for the introduction. And thank you again for joining us. So today I'm going to talk about enhancing food sustainability and continue with some of the introduction that both Graham and Daniel have presented. So let's move on. Okay, so I'm going to talk mainly about the technologies that we develop in my lab in order to fight food loss and wastage by developing novel food packaging solutions, and also take you to some of the work that we do at the Technion in order to promote food tech innovation in Israel and in Europe. So let's talk first about how can we fight food losses and wastage, and I'm going to give you some numbers that will be quite shocking, I think. So today we are talking about more than 1.3 billion tons of food that are being lost or wasted each year. And that means that about a third of all the food that is being produced today by weight is being thrown away without being ever used. So when people ask, how are we going to feed Earth usually they ask the question, how are we going to feed Earth in 2050? I think that we should all be aware that we have enough food, and Earth is very generous in providing us enough food and resources to feed humanity in 2050. The problem is that us as humans don't know how to maintain this prosperity and generosity. And we lost huge amounts. I will show you some example of food losses, and we definitely, all of us, waste a lot of resources. So this is a slide that I borrowed from the Food and Agriculture Organization of the United Nations, which tried to capture the food loss and wastage. So food loss starts even from the field, from the farm, and then it goes on throughout the entire food chain, from logistics, from packaging, from driving the food around the Earth, why we need to eat in California berries all year round or bananas all year round. This is not sustainable, right? So while everything looks very nice and fresh in Trader Joe, there is a price for that. And we also waste, not just loss, we also waste a lot of food. I'm just tell my students that every Friday we have a big fight in my house when my husband, who is a computer scientist, he sees the expiration date and then he throws everything away, and then comes the food and biotechnology engineer and tells him, oh, no, you can eat the yogurt for at least 1 more month. So we are all being, we all think and that expiration that are very, very precise, but we know that they are not. So just to give another perspective to this lack of sustainability, I want to give you a figure for the greenhouse gas emission. So if we look on the greenhouse gas emitters, so the main one is China, and then very closely the United States. But if we do the math, we can see that food loss and wastage are basically a very important country on Earth. And food loss and wastage are responsible for a staggering number of CO2 emission. So imagine to yourself that all these CO2 emitted will be directed into actually feeding people and mammals, and not being wasted. So what do we do in my lab in order to try and minimize these losses? So we are focused on developing food packaging that can enhance and increase the shelf life of food. So instead, let's look at this fresh meat, for example. Instead of that it will have only a very limited shelf life of 2-3 days, what if without adding any external ingredients, we could extend the shelf life for a week or even longer, while we maintain freshness and also assure the safety in terms of the microbial load that is present on natural food products. And how do these packaging works? So imagine to yourself that we have a simple plastic, and I will address the sustainability issues by using plastics and how we can minimize that as well. So we have a plastic bag that packs, let's say, a pound of shredded cheese. So the package itself can emit natural volatile compounds that are derived from plants, and they can actually exert natural antimicrobial effect and inhibit or kill the bacteria that are naturally growing on our food. Specifically, when we talk about cheese, we know that we see lots of molds developing on the surface of cheese, and of course other microorganisms as well. So the idea is to use volatile antimicrobials that are, especially we are focusing on essential oils and other active compounds that are derived from nature, and they are secreted into the package, and they maintain the freshness and the safety of food for a longer time. So how do we do that? So when you take such sensitive materials, such as essential oils that are derived from plants, the big question is how we can maintain their activity when we compound them or we mix them with plastic materials which are synthesized and fabricated at elevated temperatures. So the key technology that we have developed is taking naturally derived clay materials. These are excavated all around the world and are very cheap and abundant materials that have a shape of a tube. And we have developed a patented technology that allows us to load the essential oils into these nanotubes. And these nanotubes now serve as carriers, sort of small capsules that maintain the essential oils within the capsule itself for a long time, and also secrete them in a sustained and controlled manner. So by doing that, we can take these nanotubes and mix them in regular plastic compounding equipment that is found anywhere without changing the equipment at elevated temperatures. And at the end, we can have films, bottles, whatever packaging shape that you would like to have, in which we have these naturally derived antimicrobials that can be secreted when food is packaged. So just give you an example, when we don't use the nanotubes and we add an essential oil into polyethylene that is a very abundant polymer, you can see that you get a product that looks like a mesh, definitely not definitely not a film that can be used for food packaging, while when you use and mix the capsules, the nanoscale capsules, and add them to the polymer, you get a very transparent and high quality film. The important thing that we did in the Technion is not translate the technology into larger scale. It's all fun and very nice that we can produce these films in a lab scales, in a kilogram scale, but the large and very challenging step was to take this technology and produce it on a large scale. And we did it over the last 2 years, and were able to produce these films and products using conventional plastic equipment and create different types of packaging for packaging yogurt, cheese, whatever, bread, whatever you can imagine. And the next step was to demonstrate that these packaging are indeed active and can be used to, of course, inhibit and kill the bacteria that we were interested in. And we defined a couple of very important food pathogens like E. coli, Listeria, and some molds that are of importance. And we just some examples here. You can see bread rolls that were packaged in our antimicrobial food packages, and you can see the roll. It is remains fresh and free of any molds for 20 days, while the control bread, which was packaged in a regular plastic film, had a shelf life which is about half of that of the bread that was kept in our packaging. So we achieved at least 70% increase in shelf life. And what is important to keep in mind is that the capsules that we add to the plastic do not hinder the recycling process. So you can easily recycle these plastics again and again and reuse them. Another example is fresh produce, which is highly susceptible to be lost and wasted in the food supply chain. So here you can see cherries, and we have prevented the appearance of molds on these cherries and increased their shelf life by 40% and increased their shelf life by about 3 to 4 days. And now I want to shift gear from my own research to the activity that we do at the Department of Biotechnology and Food Engineering in gearing up food tech innovation in Israel and in Europe. So over the past 3 years, we have established a unique program at the Department of Biotechnology and Food Engineering, which is called the EIT Food Accelerator, the Israeli branch. And we have developed a program, a very special program for food innovators, food tech and agri-tech innovators. And they come to a summer boot camp in the Technion of about 3 months, where we educate them all on the basics of food technology and agri-tech technologies, regulations, and also provide them with mentors from the business side, from the science side, from the scientific side, and also mentors to allow them to develop as entrepreneurs. And one of the greatest examples of this accelerator activity is Jet Eat printed food. So this company headed by Eshchar Ben Shitrit, whom you can see here, was actually one of the first startup companies that joined our accelerator here in the Technion. And luckily also won the challenge in Europe, in which about 50, 60 startup companies competed against each other. And during the process at the accelerator, Jet Eat changed its name to Redefine Meat. It recently secured a funding of $29 million. And what Redefine Meat does is to print using 3D technology, 3D printing technology, plant-derived ingredients into a steak. So their products mimics the taste, mimics the texture, and the mouth feeling that we have of actually eating a steak, while everything being, while all the ingredients are plant derived. And they are doing, as you can see, pretty well, and also started some beta sites in Israel and around the world. So we are very proud of them, and we have other very successful companies that developed from this accelerator program here in the Technion. And of course, I'm sure that you know that Israel is one of the most innovative countries in terms of fake meat. So we have at least 7 or 8 companies that I know of in Israel that produce fake meat. Our own Technion Aleph meat company, headed by Professor Shulamit Levenberg, who grows cultured meat in the lab, and different and very interesting other solutions that are being developed around Israel. So at that point, I will end my presentation, and David, we will be happy to answer any questions that the audience may have.
That's really fascinating. I think that the all 3 speakers cover different parts of the current situation in the world, but makes me very optimistic that we have such smart people dealing with this. They're going to change the studio around so that they can better answer some of the questions that we have. So we'll just give them a minute to do that. But again, I appreciate all of you. We're going to go probably to about 11:15 West Coast time, so 2:15 East Coast time, because we started a little bit late. So please keep putting those questions in the Q&A function. I'll start off with a question to Daniel. You talked about the sustainability and the idea that what the campus is doing. Can you put that into context as to when you're contemplating those goals? How do you align those with what Israel's doing, and how Israel's goals, maybe Haifa's goals, and then Israel's goals, and then to the whole world goals? Are those part of one process, or how are you coming up with the Technion's sustainability goals?
I want to be completely candid with your question. One of the goals of our current efforts are to make sure that all of our waste that can be recycled get into the recycling stream. And one of the things that have prevented us from making progress is the lack of a good infrastructure in Israel in general. That is, we can organize to collect everything that we need, but we can't assure that it's going to get outside the Technion to the place where it has to be. In that case, there's an inhibitor, and perhaps we can use our market strength to, align with other universities to really push the government to organize this infrastructure for recycling to assure that products get recycled. On the other hand, there are things that the government is doing that are an incentive for us. When the government sets goals for renewable energy goals, then obviously we want to be a part of that. If we can surpass the government goals, that would be a positive result. But as it is, when the government sets objectives, it's a catalyst for us to behave accordingly. So there's a synergistic relationship in some of these, as with energy efficiency. In some ways, it can also be not antagonistic, but in a way, we're going to have to push the government forward and to make sure that there's an infrastructure outside of the Technion to allow us to do the right thing. That's, of course, on the research end of things, we're the beneficiaries of any government grants that are directed towards, any of these sustainability issues. So the more the government promotes through funding mechanisms, the more that we can take advantage and move forward as well.
Thank you. Graham, you mentioned that 1 kilogram of pharmaceutical waste creates 100 kilograms of other waste. Can you explain, like, how does that work? Why is that to have such a huge multiplier effect?
The multiplier comes from the fact that many chemical processes is not a single step. So if you want to make a pharmaceutical active ingredient, typically there are 5, 6, 7 steps that have to be, that are in place. And every step requires perhaps a different catalyst. It requires additional stoichiometric amounts of reagents. So meaning for every kilogram that you produce, you need a kilogram of an additional reagent. And we like the terms then we like to think in terms of atom economy, meaning is that the final amount of atoms that end up in your product is not necessarily the amount of atoms that you put in. Typically, the atom economy is less than 50%. You need additional reagents, you need additional solvents, you need additional stabilizers in order to get to your product. And these multiply from step to step to step. So you can see that if you have already 5, 6, 7 steps, which is actually quite low, is that the amount of waste increases exponentially after each step. So the key is really, can you define more sustainable processes or catalytic processes that typically become, let's say waste neutral or do not generate any waste? And if you do, can we reuse it? So that I think this is where the waste comes from and where we can actually gain, where there's a lot of gain to be made.
Thank you. Your comments about the catalytic converter definitely resonates with us here in the U.S. because we're seeing a lot of that theft going on. So hopefully we can find a way to cut back on that. As a lot of people are interested in this plastic that you're creating. So maybe you can talk a little bit about, two big questions are, is it more costly? What's the cost are we talking about from a scale perspective? And also you mentioned nanotechnology, and there's been a lot of negative press about, nanotechnology, especially from shampoos and things like that ending up in the ocean. Is this contributing to that problem?
So I will start with your second question regarding nanotechnology. So all this work was conducted through a European grant that we initiated and received in the Technion. And one aspect was to also study the consumer acceptance towards such nanotechnology solutions. And we were surprised to learn that at least in Europe, which is sometimes significantly more conservative than in the United States, people think that if they can increase and preserve the freshness and safety of their food, they will use nanotechnology solutions. And also it is important for them that we as scientists will explain what is the nanotechnology solutions that we are using. So I didn't emphasize it enough during my presentation, but the nanotechnology that we are using are actually clay materials that are naturally derived. You can find a lot of them in Utah, actually. So these minerals are not only abundant and cheap. To give you some price, we are talking about $4 per kilogram, and we only add about 1% of them into the plastic material. So the added price into the final price is low and definitely cost effective. And we also did extensive toxicity studies, learned how these nanotubes affect the aquatic systems and other ecological ecosystems. And we showed that these materials are completely inert. They never leave the plastic material. So in terms of human safety, they are encapsulated and kept within the plastic. They are not secreted. And even if they are secreted, they are completely safe. So these two topics really
Can the bags be reused?
The entire development process.
Can the bags be reused? That was another question we got.
Used, they can be recycled, and we also add these additives into biodegradable and naturally derived plastics. So it's not limited. We don't have to add them only to synthetic plastics. We can also add them to naturally derived plastics as well.
Great. Well, definitely a lot of interest in this topic. So I'm sure that there'll be more questions coming on it. Back to Graham. We have a question, kind of a more general question. How do you collaborate with industry, and how does research in industry versus the universities differ to create more efficient processes? So how is that collaboration going? Are you working with industries that are doing similar research? And are you being complementary, or are you being parallel and then collaborating? How's that working?
So we do work with industry. I recently only started at the Technion, so I'm about 3.5 years here. So my network is not that extensive. We had preliminary talks, for instance, with Fujifilm, who was also a big in catalysis and chemical industry, to talk about some of our new inventions. So yes, definitely, there is a lot of crosstalk between industry and academia. I think there is a lot of collaborative research, but it's directed in certain things. I think that in the academia, you have a little bit of more freedom to explore different options that the industry doesn't have. Because in the end of the day, in the industry, you do have to make profit, and you do have to research relevant research directions that are relevant to the industry or to the market. And that definitely you do not have in the academia. So it's easier for us to tackle harder problems that run over longer period of time to solve than the chemical industry does. And that's why I think the collaboration is such a great one, because they can outsource projects to the academia, and we can address it, let's say, with 3, 4, 5 graduate students over time, which the resources in the industry do not have. Overall, of course, my research is also directed towards basically generating or finding more sustainable processes that are beneficial for society, but also for market, because it's not very useful to optimize a process that is being used on a very small scale. That's not where you're going to make the impact in general. So we are complementary, and we are able to address different options depending on the interest. So we have a little bit more freedom, but it allows us to address different projects or different problems that the industry might not have the time or resources to allocate for. And that's why the collaboration is so useful.
Thank you. Back to Etsy, we have another question interested in the meat, the meat, and talking about cultured meat versus other ways of producing plant-based meat. Might be, someone's commenting saying that it might be more resource intensive, but it's also an easier way to reproduce meat-like texture. Is that true?
So this is a very, I would say, complex question. I think that the market towards meat alternatives doesn't always come from a sustainability perspective. It also comes from people who are against consuming animals. So they would rather, I would say, invest in technologies that can be sometimes more demanding in order to get meat substitutes. In terms of, I have to say that in terms of other alternative proteins that are not produced in the lab, like cultured meat, we are talking about the solutions are mostly more sustainable than meat, because the environmental carbon footprint of meat is, especially red meat, is unimaginable. Actually, any other protein is more sustainable than red meat. Eggs, chickens, and of course soya, which is only a fraction of the footprint of red meat. And as for the cultured meat and its footprint, you know, you don't have a process yet that is industrialized. So it's very difficult to do a proper calculation of the environmental footprint of these solutions, because it's not industrialized yet. And of course, this will be needed to tackle and address properly once such processes are available.
Great. I think we're running short on time, but I want to bring it back to the US. We've had a couple of questions about how does your research going to be impacting the United States? And so I'll go back to Daniel first. And start and say, you know, where you see where we might be seeing in the US, we might be seeing some of your research impacting what's going on here.
I want to think about this to answer it correctly. Obviously, the theoretical components of all my research, and I didn't talk about all of my different research projects, but the theoretical component is always transferable to other systems. I'll just talk about one particular part of my research program that I didn't present now, which is socioecological research is a methodology as well as a discipline. And when I say methodology, it's built on the assumption that you should do policy-oriented research in collaboration with local people, with stakeholders, with policymakers. That is, you do your research as a community, not just the researcher, but also the people who are going to be impacted by the research. And that type of methodology we're implementing across Europe and also the United States. In Baltimore and Arizona, there are two examples that I work with some of the people there, where really they analyze the system, the ecological system, with humans as an intricate component of that system. And they do it in collaboration with the various communities. And it produces much more sustainable outcome when the researcher is working with the people who are also providing information from their day-to-day lives about sustainability issues. A lot of times it's agriculture, but oftentimes it's pollution, urban pollution or otherwise, that you have an automatic collaboration between scientists and communities. Then the result or the outcome or the recommendation is the product of that collaboration. And there's more cooperation than when you say, scientists come and say, no, 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 you're doing it wrong, you have to do it like this. So it's not always the best solution that the scientist would prefer, but it's a more sustainable solution because the community is already built into the research process. And this is particularly important in an age when we have increasing misinformation and distrust in science. This is the reverse process that's going on in a lot of places, including the United States, where citizens and scientists are drawing apart this collaboration of transdisciplinary research brings people together and increases trust in science. So I didn't talk about that this evening, but it's certainly an area where it has broad implications for how science is done also in the United States.
Well, we're going to I'm going to be tracking what's happening with the wild boars in Haifa, because we have a deer problem here in where I live. So I'll be interested to see what lessons we can learn from that. But Graham, what about your research, and how's that going to be impacting the United States?
I think it is not only impacting the United States. I think it has a global impact, because the reason is that the chemistry that I'm doing in Israel is no different than the chemistry in the United States. Meaning the chemical processes that we're using here are the exact same chemical processes, more or less, in the United States as well. So any gain, not only in Israel, that is being made anywhere on the planet, is a gain that you also make in the United States, as long as the technology becomes available. And meaning that my research of using earth abundant metals properly, properly licensed or commercially available on whatever means necessary, for instance, can be used in the United States, can be used in Europe in the exact same way. And I think that's the beauty of exact sciences, because it's independent of the country where you are. One thing that I'd like to add is, and I think it shows in the different types of research that we're all doing, we can do as much as we can. But if there is no change in attitude, in my opinion, from the general public, much of those efforts also will be partly in vain, because I don't think we would have such problems, let's say, with plastics, if people didn't use it once and throw it away, right? Because overall plastic can be, to a certain degree, quite sustainable if you keep reusing it. And that's not what we're doing. We're just throwing it out. And that's actually the consumerism, and that's not only in plastic, it's what we see with food as well, right? The issue is not the materials that we have, it's how we use it. And I think there's a lot to gain as well. And in the meantime, I think we all three try to solve problems that can benefit society overall, and particularly also the United States. And in chemistry, because it's global, there is no difference of where we do the science. It's the same everywhere.
Great. Etsy?
Yes. So I think that my research is really focused on applicative solutions. I think many of us here in the Technion are focused on applicative solutions. So as Graham said, anything that we do is translatable to everywhere on Earth, like Japan, of course, the United States.
Well, you mentioned that us in California, we like to have our berries and our fruits and things like that on a year-round basis. Is that something we're going to have to get used to not doing?
It depends. It depends on your decision, right? My kids who lived in Southern California for a couple of years still think that berries grow in California all around the year. They don't understand why in Israel they are available only for 1 month. They still think that something is wrong with Israel. So go convince them.
Great. Well, this has been really fascinating. I think we are out of time, a little more out of time, but I think we could be talking about this for the rest of the evening and the day. But it's been really a really incredible conversation. Appreciate all the interesting research you're doing, not just that bringing it to the academic world, but also, as we heard about, the commercialization. And that's really, I think, what the amazing thing that Technion does is not only creates fabulous ideas, but puts these ideas so that we can use them. All these topics we talked about, will have major impact in how we live our lives going forward, how we work, how we live, how we play, and that's what's been so excited for me getting involved with the Technion through the ATS, and look forward to doing more with that. The recording of this will be going out, so if you don't have to be taking notes and things like that. You will have the recording that you can go back and watch it again. And if you have any questions, something we didn't answer, we'll try to get that to you. I think we've been taking notes of what's been going on in the Q&A that we couldn't get to. But if you do have any specific questions, please reach out to us. You can reach out to me, dkaufman@nixonpeabody.com. I'm happy to get those to the people. But it's been really a delight to talk to our three fantastic speakers and speak to you all today. So stay safe, stay healthy, and look forward to seeing and talking to you all very soon. Thank you. Good day.
Thank you.
Thank you.